For 20C, using the following data and information from the HR diagram, show that star A is at a distance of about 800 PC from Earth. So, looking back at the graph of where star A was located on the HR diagram, you saw that on the chart, the luminosity was 10 to the 5th. So with it being 10 to the 5th, you multiply 10 to the 5th times that, what we did earlier with the Wien law. So it will be the apparent brightness of the sun per the apparent brightness of star A, and then you divide and multiply this out, and it gets like 1.7 times 10 to the 8 AU, which is 800 PC. And then for 20D, you have to explain why the distance of star A from Earth cannot be done by the method of stellar parallax, and the parallax angle is too small to be measured and measured accurately, and the distance is greater than the limit for stellar parallax, which is 100 PC. So any answer between 100 to 800 PC will be acceptable. I just put 670. So with 8, part A with the D2 PDF, they state what is meant by a binary star system. 2 stars orbiting about a common center of mass or gravity. B, part 1, is asking about calculate like the two Alpha Centauri, like A and B. So wait, the apparent brightness of them. So because they showed us the luminosity, I just divided the luminosity of A and B, and I got 3. Now the luminosity, so part B, but the second part of it, the luminosity of the sun is 3.8 times 10 to the 26 W. Calculate the radius of Alpha Centauri A. So I put the luminosity of the sun over the radius over the surface area of the Alpha Centauri. So the 4 pi and the D, and then the 5.67 times the -8. I got that from what was provided to. And then at the end, after I do that, I got 8.4 times 10 to the 8 meters. Remember your units. 8C was show without calculation that the radius of Alpha Centauri B is smaller than the radius of Alpha Centauri A. They both have similar temperatures, so you're trying to look for a ratio to make things easier. So I used the ratio from the luminosity, and that was similar to what I did with part A, being 3, and it's a significant difference from B and A, B being 0.5 and A being 1.5, and then I was able to see that the radius is Alpha Centauri B radius is less than A. 8D, Alpha Centauri A is in equilibrium at constant radius. Explain how this equilibrium is maintained. I said forces and pressures are balanced, so gravitational and inward forces and etc. Now for E, for number 8, I had to use this thingy. Looking at the luminosity and the temperature of Alpha Centauri A, because you have to use the HR diagram and draw the present position of Alpha Centauri A and its expected evolutionary path. This is the expected, this is where it's supposed to be. You understand me? The location of Alpha Centauri, right here. And then this is the expected path to go in the circle, which is the region of the white dwarf. Because, yeah, this is evolutionary path. Now, for D2, that PDF, 18, a Cepheid star and a non-Cepheid star both belong to the same distant galaxy. Explain, stating the quantities that need to be measured, how the luminosity of the non-Cepheid star may be determined. Measure a period of the Cepheid to determine its average luminosity. You will measure the apparent brightness of the star, and it gives you the luminosity, because you already know apparent brightness, and then the equation is like the luminosity of the star and over the luminosity of the sun. Now for D3, D.3, the PDF, I had 6A, identified the two characteristics of the CMB radiation that are predicted from the hot Big Bang theory. Black body radiation, which we should know, and the isotropic, so it appears the same from every viewing angle. Those are the two characteristics, and even another one was like homogeneous, things that stay the same throughout the universe. And then 6B was a spectral line in the hydrogen spectrum measured in the laboratory today. It has a wavelength of 21 centimeters. Since the emission of the CMB radiation, the cosmic scale factor has determined by a factor of 1100. Determine the wavelength of the 21 centimeter spectral line in the CMB radiation when it is observed today. So because of the factor, you're going to do the 1100 times the 21 centimeters, and you multiply the 2, and it gives you 23,000 centimeters, and then you can convert it into 231 meters, because you just divide 23,100, divide that by 100 centimeters, and it gives you the 201 meters. And that's it. That's the end of my astrophysics video explaining the questions that I had. Thank you.